I'm back. We're going to talk about another fundamental calculus operation in a context of physics, again, for which calculus was developed. Anywho, let's talk about an object whose velocity varies via this function, and our task is to find this object's average velocity over a certain interval from 1 second to 4 seconds. Here's the wrong way. Why I tell you the wrong way? Because people do this all the time. There's wrong. Well, let's see. I can do that V average is V final plus V initial over 2, right? Isn't that a way that I learned to do average velocity? Well, that works only if velocity varies uniformly at a constant rate. You know, that's easy. If velocity as a function of time is constant, its average is trivial. If velocity as a function of time varies uniformly or at a constant rate, then its average is the middle of that function, which you can find via that process. But this is not a linear function. And thus, you can't simply average initial and final values. Okay, what you have to do, well, if you remember, well, if you saw a previous video, this function, v as a function of t, does something like this. Well, I know that when t is 0, we can put 0 in for both of those. We get a velocity of 0. I know that this function starts looking sort of negative and linear because when t's are small, cubed t's are really, really small. So for small t's, I'll say, quote, small t's, well, that negative 2t term, its magnitude, is larger than the 4t cubed term. Right? Again, you cube small numbers, they get really small. But for larger t's, quote, large, that's junk to say, but you know, let's just sort of speak qualitatively here. For large t terms, the opposite's going to be true. The negative 2t term is going to have a much smaller magnitude than the 4t cubed term, because as you can likely imagine, when you cube large numbers, they get really, 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 really large. Okay, so this function's going to look something like this. It's going to look like well, that's a line, right, of slope negative 2 for a bit. And then it's going to turn into a cubic upward, because that's a positive. So this function looks something like that. Okay. So let's see. Okay, so we want to find this function's average value. Okay, we want to find the average velocity. Well, here's what you have to know. Let's see, average, what's the best way to say this? The average velocity is, I'm going to do this in the range that we have, this function probably does something like that. Okay, so this average is probably, I don't know, it's something. So really qualitatively, maybe its average is about here or so, right? There's maybe V average, maybe lower than that, I don't know. But, well, look, if this is the time interval here, I'll call it delta t, or here's our time interval over which we want to know that average velocity. Well, look, if we were to do average velocity times that time interval, right, that's this height times that base, what we would find is the area under that function. Okay, and the area under that function, this V average times delta t, well, by definition is delta x. It's this object's displacement. So to do that, to find V average, what we did was, in this case, well, we just do definitional old-timey average velocity as rate of change of position. Okay, well, what we have to do with this function is, I mean, we still know a time interval of 3 seconds. If we could, from this function, find the change in position, well, then we could find, apparently, we could divide by that time interval and still find the average velocity. So the question is, how do you find a change in position from a velocity function? Well, by definition, here's what we're sort of, here's an actual calculus lesson. Like, well, look, in this little amount of time dt, tiny little amount of time dt, not a macroscopic time interval, but almost an instant, but it's some amount of time still, because the amount of time has to be an amount of time. Well, look, the function, the function, I can't zoom in anymore, but this function has, you know, an average value over that little dt, but that average value is basically, the average value of the function over little interval dt is basically the value of the function itself. Okay, and so this little area is a little, well, it's a little v at instant t, which is basically the average, the same, approximately the same as the average value of the function over this dt. Well, times that dt gives us a little tiny dx. Now, little tiny dx is not the macroscopic change in position, but what's true is that the change in position is the sum of all the little tiny changes in position. And that's, in effect, what integration means, or an integral is it's adding up, adding up all of the tiny little things. So a macroscopic change is the sum of all the microscopic changes. And look, we just defined how big one of those microscopic changes is. It's the value of the velocity function at time t, at any instant, times a little time interval. Now, what we have to do is say, so what we're actually doing in this procedure is saying, well, let's find this total area, if this is our 3 seconds, like right now, what we're saying is let's find this whole area. It's actually this area minus that area. And that's going to be the same as the red area, because those areas are both changes in position. And again, if we can find that total change in position, then, quote, all we need to do is divide by the time interval, and we can find the function's average value, which is our Mandy. Okay? So now this becomes, now what we have to say is we can only find an area, an actual change in position over a defined interval, and that interval is from time equals 1 second to time equals 3 seconds. These are called the limits of integration, and they are AKA minimum and maximum value of time, and there are times because we're integrating with respect to time. And so now the question is, how do we do this? And well, that says we are going to integrate over these bounds, or between those bounds, this function v as a function of time. That's 4t cubed minus 2t. We're going to integrate that with respect to time. And this is called a definite integral. Because two reasons. One, we're finding an actual answer. We're not finding a function, we're finding a number. And therefore we have to use these limits of integration. So now, all right, how do you integrate? Well, integrate is we can now think of it as the opposite of differentiation. So it's like we take the antiderivative of this function. We need a function whose derivative would be this if we took its derivative with respect to time. And so the way that we do that, look, here's notation. Here's the integral. The integral is, all right, this number's got to go up by 1, so that's t to the 4th. And here was the original 4 from here, right? But watch, if we had taken the derivative of 4t to the fourth, we'd get 4 times, we'd get 16t, but I don't want 16, I want, so it must mean, here's that original 4, it must mean that we have to divide by a 4. Right? So what we're saying, in the simplest way I can say it, is the integral t cubed dt is t to the fourth over 4. Right? Generally, we say that if there is a function f of x equal to ax raised to the n, then the integral f of x with respect to x is a over n plus 1 times x raised to the n plus 1. That's what you do, right? You have to knock that number up by 1, but you have to account for the fact that if you were going to differentiate and you multiplied this n plus 1 times that stuff, you'd still want to only end up with a, so that's why this 1 over n plus 1 goes there. Okay? So, yes, 4 over 4t to the fourth, I understand that that's simplifiable, plus, let's see, well, this is going to be 2t squared over 2. Now look, here's notationally correct stuff. We are integrating from 1 to 3, which means I have to evaluate this function from 1 to 3. Notice, now that I have taken the, now that I've, here I'm saying I am going to take the, I am going to integrate this function, right? Now I have integrated the function, so there's no more integral here because we have integrated. All right, so now we can say, all right, let me just simplify. This is, I did so well here, thank you very much. T to the fourth minus t to the second. Hold please. Evaluated over these bounds 1 to 3. Well, here's what that means we do. First, we say, okay, well, we put first 3 into each of these. Put 3 in for each of the t's, so we get 3 to the fourth minus 3 squared, and then we subtract, and we put these in. So we subtract 1 to the fourth minus 1 squared. And guess what we're doing? This is actually, look, this is x final. I'll put the little f. It's the position evaluated at time 3 subtracted by the position evaluated at time 1. So this is the delta x. That's why that's delta x, because we are evaluating a function at 2 different instants. Well, I happen to know that delta, this means delta x is, well, all this stuff is 0, right? That's 1 minus 1, fine. 3 to the fourth, let's say 3, 9, 27, 81 minus 9. Those are both in meters, they must be. So this delta x, embarrassing if this was wrong, but I'm pretty sure it's right. Yeah, it's right. Is 72 meters. Oh crap. Well, let's just notice, buddies, I did this wrong. Okay, look. I said from 1 to 4 seconds. You want me to, why don't I, I'm going to change, yeah, I'll do it. I'll change it to a 4. Why wouldn't I? There's a reason that I'm going to make that change and not change the other thing. Okay, sorry. 4. Okay, 4 to the fourth, that's 16 times 16, that's 256 minus 16, fine. So that's 240, fine. Okay, we're not done, right? We have to do, our question is, what's the average velocity? So what we are doing is saying, okay, the average velocity is delta x over delta t. Well, that's really the definite integral from T1 to T final, T to T final of V of T with respect to time, all divided by the time interval. Well, this is the T initial to T final of the V with respect to T. So we have done this to get this number 240. We divide by our time interval of 3 seconds, and we get an average value of 80 meters per second. Okay. Look, here's the actual function. Yeah. Look. This is, I don't know. Look, we have coefficients and exponents. 0 y to the, or t to the fourth plus 4t cubed minus, this is the actual function, and it's over the interval from 0 to 3 seconds, and so this says its average value is about that. Do you buy it? I don't know if I buy it. I think I did something wrong. You should have seen me banging my head against the wall about what did I do wrong? Look, remember I said this is the function. This is the real function. Look, I only did it over the interval from 0 to 3. I want it from over the integral from, actually want it over the interval from 1 to 4 seconds. Right? Remember, that's what we were trying to find. And look, so we said average value is about 80. Yeah, that I can buy. I can buy that all day. Right? You dig? So I made a goof on my graphic over here. Our delta t is really only from, like here over, that's it. Well, it's not from all the way from the x-axis. But, okay, good. So our process is certainly sound. All right, let me remind you of our process. This is how you solve this problem. Okay, when you want a function's average value that does not change linearly, what you have to do is find, this is the total area bounded by the function and the x-axis. So important, that's important to note. That's really what integration does for us. This is area this is divided by base, right? And what does area of a shape divided by base get you? Well, it gets you its average height. And that's what we want, right? We want this function's average height. So we take this definite integral of the velocity function with respect to time over the time interval that has been defined for us from 1 second to 4 seconds. Right? Here's a bit about the algorithm of doing antiderivatives. Right? Notationally, we say, look, now we say let's evaluate this function over the interval from 1 to 4 seconds. That's what this bar means at the end. We are evaluating at those two bounds, which means we substitute the top bound in and evaluate, and we subtract when we substitute the bottom value in. Right? Remember that integral gets us, this integral gets us the change in position, which we get as 240 meters. We've got to divide by our total time interval to get our average velocity. Okay, buddies? There it is. That's another calculus fundamental in the context of physics. Thank you.